Good evening everyone. Today we are going to continue where we left the other day, talking about distribution of mineral deposits in space and time. Today we will specifically deal with time factor. Ore deposits are extremely rare occurrences. Combined natural processes of igneous, sedimentary and metamorphic processes and tectonic activity have carved out ore deposits of widely different sizes, shapes and kind out of the commonly available starting material, the normal earth composition. We are also aware of the fact that geologists believe that the entire geological column from Archean to Quaternary is a very long period, geologically speaking. Hadean through Archean, Proterozoic, Phanerozoic to the present. The question that may naturally come to mind of a layman or even an undergraduate student of geology is when were all the mineral deposits formed? Were they all formed at the same time, geologically speaking, or certain era, period, epoch or age were most favorable for formation, deposition of certain deposits? This is a very interesting and relevant question for students of geology and professionals whose job is to find future mineral deposits. We may never be very specific regarding the exact time of formation of a deposit, but the approach and scientific thinking is valid. In this talk, we will continue our theme of mineralization through space and time, its relation to specific areas, that is space, we have already dealt with. In this talk, we will consider if and how geological time has much to do with mineral deposits. We shall consider this theme under the following heads: mineralization, rock association, space and time. Second, global picture, mineralization through geological time. 3. Metallogenic epoch in India, Precambrian, then metallogenic epochs in late Proterozoic. 5. Metallogenic epochs in late Mesozoic through early and the present. In module 1, we shall see mineralization, rock association, space and time. If for the time being we forget about control of time and space on origin and occurrence of mineral deposits, there is an unequivocal observation that many mineral deposits occur with only in association with certain specific rock types. Coal and oil are never to be found in igneous rocks nor chromite with acid igneous rocks. Ultramafic rocks like dunite, peridotite are home to chromite and sedimentary rocks to coal and oil pools. A large number of associations could be cited, but to prove the point, the following will suffice. Under the igneous category, in ultramafic rocks, we have deposits of chromium, cobalt, nickel and copper. In mafic rocks, titanium, vanadium, scandium. In alkaline rocks, we get titanium, niobium, tantalum, phosphorus and fluorine. In carbonatites, rare earths, tantalum, niobium, titanium, phosphorus, fluorine. In granitic rocks, barium, lithium, tungsten, molybdenum, tin, uranium, thorium, zirconium, hafnium. In pegmatite, lithium, rubidium, cesium, beryllium, rare earths, niobium, tantalum, uranium, thorium, zirconium, hafnium and scandium. In sedimentary section, under the black shales we have uranium, copper, lead and zinc. Phosphorites we find uranium, molybdenum and vanadium, and in laterites nickel, chromium, vanadium. In continental red beds we may find uranium, copper, molybdenum and lead. In bauxites niobium, titanium, gallium. Next thing is, as we have seen is one of the previous talks, what we call the tendency of ore deposits of a particular metals or a particular style of mineralization being restricted to a very large area, that is called a metallogenic province. Thus, all over the world we hear of gold province, copper province, chromite province, iron ore province and the famous tin province of Southeast Asia and Eastern Australia and also Southern Europe. A characteristic feature of such provinces being recurrence of ore forming processes may be of different intensity a number of times geologically speaking. This last feature is the theme of this talk, referred to as metallogenic epochs. This would be called a specific period in geological history when large number of deposits of a metal or metals or mineralization of a typical style were formed. This does not mean that the particular ore mineral would be totally absent from other epochs. The point is, metallogenic epochs is that period when it was formed overwhelmingly to that extent that it will become a characteristic feature of that epoch. Early to middle Proterozoic is therefore rightly called a metallogenic epochs for the formation of world famous banded iron ore formations round the world. This does not mean that the Archean do not hold any BIFs, they do, but its best development was during 2500 to 1900 million years ago. In module 2, we shall see the global picture, mineralization through geological time. Earth scientists believe that long geological span from Archean to the present has been many drastic and potent changes of temperature, pressure, tectonics and chemical environment. It is but natural to believe that these must have had powerful influence on their ability to generate not only specific kinds of rocks, but associated specific ore deposits also. Such an idea has given the concept of metallogenic epochs, which the American Geological Institute defines as a unit of geologic time favorable for the deposition of ores or characterized by a particular assemblage of mineral deposits. Several metallogenic epochs may be represented within a single area or metallogenic province. In the earlier talk, Mesozoic era was the time for almost all the deposits of the world Precambrian specific 2500 to 1900 million years interval. For banded iron formations of the world, in this module we will have a bird's eye view of the ore deposition through geological time, considering only the major units like the Archean, the Proterozoic and the Phanerozoic. In the Archean, this major part of the geological column, as believed by geologists lasting 3800 to 2500 million years ago, not only has some characteristic and unique mineral deposits, but also lacks other important ones. Petrologically, it can be divided into two parts: the lower grade, metamorphically speaking, greenstone belt, and the high grade gneisses and granulites, etc. Both have somewhat different kinds of ore deposits. The Archean in general are the storehouses for deposits of chromite, PGM, iron nickel deposits, gold and also some VMS. Among the greenstones, gold, silver, copper and zinc are hosted in volcanics, mafic to felsic in composition, while chromium, nickel, copper are associated with ultramafic flows and intrusives. Rare metals like beryllium, lithium, niobium, tantalum, tin, molybdenum and bismuth are within granites and pegmatites. Iron and manganese ores are the identity of the Proterozoic, but they are not totally absent from the Archean like in Western Australia, Canada and more significantly BIF in China, hosted both in greenstone belts as well as gneisses, making it a rather peculiar occurrence, while still retaining lake superior character. Under the Proterozoic, we have the entire Proterozoic eon, late, middle and early, has been a very productive time from mineralization point of view on a global scale. Most extensive and characteristic of the early to middle Proterozoic are the banded iron ore formations of Lake Superior type from USA, Canada, Pilbara, Western Australia, Krivoy Rog in Ukraine and Kursk in Russia, Brazil, South Africa and of course India. Gold uranium conglomerates of Witwatersrand Basin, South Africa, as also Lake Huron, Blind River area of Canada, those of Australia, Brazil and Chad sedimentary. In sedimentary metamorphosed manganese deposits overlying the Transvaal system, South Africa, West African deposits of Ghana, the Ivory Coast and Gabon are good examples. Titanium iron bodies of Norway and Canada and chromium, nickel, platinum, copper combination in large dikes as that in Zimbabwe and the enormous layered complex of Bushveld, South Africa are the important sources of chromium and platinum. Finally, the source rock for diamond. The kimberlites were also heralded their explosive entry into the cratonic areas of the world around this time. In middle to late Proterozoic, we have the characterized by the presence of nickel deposits of Canada, Manitoba, sedimentary copper ores of Zambia and northwestern United States, famous gundite associated manganese belt of India, Brazil, Russia and Namibia. They may or may not have interbedded BIFs with them. Tin belt of Africa and western Brazil within alkali granites pegmatites is yet another important mineralization of this time. Lastly, gypsum deposits and other evaporites and some algal derived coal beds are also the products of late Proterozoic. Coming to Phanerozoic, the Carboniferous, the name is derived from English stratigraphy where rich coal deposits exist, period lasting for over 100 million years, 359 to 299 million years ago, is the most favorable coal forming era globally. Rich coal deposits of northern Europe, midwestern and eastern United States and Asia, including those of Indian subcontinent, are the best examples. It was most favorable time since the land was richly covered with swamps where huge ferns and other large trees supplied the vegetable matter, the source for coal. Some deposits of coal, though on a much, we may thus conclude that Mesozoic and Cenozoic periods were the most favorable for the origin of hydrocarbons. However, there are evidences that even from recent marine sediments like Gulf of Mexico, of Louisiana and Santa Cruz Basin of California, hydrocarbons have been forming. According to one estimate, 4,500,000 to 10 million barrels of crude oil per cubic mile of sediments are present in these areas, according to Mason and Moore. Among metallic deposits, Phanerozoic was the time of podiform chromite, huge deposits of volcanogenic massive sulfides, porphyry, copper, molybdenum, as also gold, associated with subduction zones and island arcs. Phosphorite, though not unknown in Proterozoic, show their maximum development in the Phanerozoic, commencing right from the Cambrian Phanerozoic boundary. China, Kazakhstan, Vietnam and Australia have large resources. In fact, almost all the continents have phosphorite sequences in Phanerozoic. Residual clays and bauxites derived from alumina rich rocks tops the important list of resources of the Phanerozoic, in particular in the Cretaceous to recent time gap. In module 3, we shall see metallogenic provinces in India, Precambrians. Undoubtedly, The Precambrian epoch has been most productive in generating a large variety and number of important mineral deposits world over due to the combined forces of magmatism, sedimentation and metamorphism over longest part of the earth history. Our country is no exception. Among important deposits, the first that comes to mind is our celebrated iron ore deposits in the states of Jharkhand, Orissa, Chhattisgarh, Maharashtra, Karnataka and Goa, followed by manganese ores, though not so extensive, nevertheless important among global mineral resources, concentrated in Balaghat, Nagpur, Bhandara triangle of central India, as also various places in Karnataka, Tumkur and Dharwad, a few in Gujarat like Panchmahal and Vadodara. Chromite of Singhbhum, Jharkhand, Khaunjar, Cuttack and Dhenkhani in Orissa, Bhandara and Ratnagiri in Maharashtra, and important deposits in Mysore and Hassan in Karnataka, and of course gold of Kolar, Hatti and Gadak in Karnataka, and those of Andhra Pradesh, Ramagiri and Anantapur district come next. Our base metal resources are comparatively smaller in size and lower in grade and include deposits of copper, deposits of Singhbhum, Khetri, Kolihan, Purbanera, Bhindar, all in Rajasthan, Agni Gondala, Malayam and Gani in Andhra Pradesh, Balan Khan in Madhya Pradesh, and those of Karnataka, Ingaldalu and Kalwadi. Lead zinc in Rajasthan like Agucha, Rajpur Dariba, Deri, Banaskantha in Gujarat, and those of Orissa in Sargipalli and Keshpur and Karmali were all formed during the Precambrian epochs. In module 4, we shall see metallogenic epochs in late Proterozoic. This epoch in particular, Permo-Carboniferous time gap, is characterized by organic and sedimentation on a large scale, and this is the time when swampy areas with thick vegetation were converted into rich coal seams. In India, coal deposits were formed for the most part in the lower Gondwana, that is upper Cretaceous Permian. The coal bearing strata were laid down in about 75 basins in the Indian peninsula. The larger basins include Raniganj, Talcher, Bokaro, Ramgarh, Northern Karanpura, Sohagpur and Singrauli. The important coal bearing formations are known collectively as the Damudas, that is lower Gondwanas. The source material on the basis of plant fossils for Indian coal as also for those of South Africa, South America and Australian is considered to be Glossopteris flora, which was most common during that time in the vast southern hemisphere known as Gondwana land. Presently, their distribution is not uniform throughout the country, but aligns with present river valleys and derive their name from them. The main among these are Damodar Valley Belt, Rajmahal Birbhum Belt, Satpura Son Valley Belt, Mahanadi Valley Belt and Godavari Vardha Valley Belt. The entire coal belt has witnessed hyperbasal intrusive activity in the form of dikes and sills of basic to ultra basic composition, in particular lamprophyres. They may be the source of a number of minor and trace elements in future. The entire coal belts is also endowed with large amounts of clays, I mean the fire clays, ochres and ironstones, which have their own economic importance. Apart from the main coal forming event of lower Gondwana, tertiary coals make a very small percentage of India's coal reserves, but nevertheless these are important locally. These are mostly confined to the northeastern states of Assam, Meghalaya, Nagaland and Arunachal Pradesh. In module 5, we shall see metallogenic epochs in late Mesozoic through tertiary and the present. Mineralization of copper, chromium, nickel, zinc and lead, magnesite, fluorite and asbestos associated with plutonic and volcanic activity, and in particular with the ophiolites, is present in the extra peninsular regions. The deposits are not very large, but nevertheless present. The regions include the Himalayan Ladakh area, Manipur, Meghalaya and Andaman Nicobar Islands. Our oil and gas resources also belong to this period, namely tertiary, that is Eocene, Oligocene, Miocene epochs. Though oil gas fields of Rajasthan may be of early Cambrian to tertiary age, residual deposits of clays and in particular bauxite were also generated during this epoch, though their formation was also a factor of suitable source rock and climatic conditions, mostly favored by tropical climate. There was stupendous basaltic flood eruptions during the KT boundary, which have covered a vast area of western and central India, blanketing early geological formation along with their whatever mineral resources. In return, however, the Deccan basalts have yielded rich and fertile black cotton soil, which has been the continuous source of agricultural productivity, maybe for over 10,000 years. Apart from its use as building material and road metal, there are sporadic occurrences, not deposits, of native copper in them, as also some secondary silica minerals like amethyst, agate, chalcedony, carnelian and others, as also pockets of montmorillonite clays and huge quantities of laterite. The Deccan Trap, particular of Maharashtra region, are also the storehouse for beautiful zeolite samples. Lastly, many placer deposits like gold, diamond, cassiterite, monazite, etc. would have formed from geological past up to recent times. Coming to the summary of the entire lecture, ore mineralization was not an erratic phenomena. During the long history of the earth, specific time periods were responsible for specific kind of mineralization. This does not rule out formation of these ore deposits in other times, but that period of time when these deposits were formed overwhelmingly is what we refer to as a metallogenic epochs. The specific region where these mineral deposits abound is what we call a metallogenic province, and together they make a common theme of distribution of mineral deposits in space and time. A bona fide metallogenic province would have witnessed a number of metallogenic epochs. If one have to give just three representatives of examples, metallogenic epochs, the first one will be undoubtedly chromite and gold deposits during the Archean, banded iron ore formations and manganese ores of Proterozoic, and coal deposits of the Carboniferous. Intelligent use of the concept of the distribution of mineral deposits in space and time undoubtedly is the first approach to the important exercise of mineral prospecting in future. Thank you.